Great, so in this session we're looking at scatter plots and correlation, which I know that you've seen this before, right? You're coming out of Algebra 2, FST, you know what a scatter plot is. You've done problems with correlation before. You've done linear regression, line of best fit, that sort of thing, like going back to like 8th grade. Okay? So that aspect is nothing new. What is important for us in a statistical sense is kind of looking at it from this statistical perspective. Okay? A lot of this class is not so much about the calculations, it's more about the interpretation of what's going on. Okay, so we're in this section, and then in our next section when we start talking about the regression analysis itself, we're looking at it through that lens. Okay, so we've got our targets today, explanatory and response variables, creating and interpreting scatter plots, using correlation to describe the relationship between two quantitative variables. So I think I've already used these words to describe our variables, but explanatory and response. Okay? We have the x value is like the explanatory, and the y value is like the response. And you can think of that as there's an x in explanatory. But we use these terms, okay, with the idea of the x value possibly explaining the y value. I mentioned we're talking about correlation today. I'm sure you've heard that phrase before, that correlation does not mean causation. And that is true. That's important. That's a big thing about what we're discussing in this unit with the conclusions that we can make. Correlation does not imply causation. The relationship between the explanatory and response variable, though, you can take that liberty a little bit in thinking that, well, if there was a cause and effect relationship, it is the x that is causing the y, or it is the x that is explaining the y. Okay, if that relationship truly does exist. In algebra, you refer to this as the independent variable, and y as the dependent variable, right? If you have an equation like 2x plus 1, y equals 2x plus 1, whatever I put in for x, that dictates what's happening with y. So x is the independent, the explanatory is the independent variable, y is the dependent variable. It depends on something else. Well, we don't use those words in statistics because when we start talking about probability, independence and dependence, that has an entirely new interpretation that we need to be careful of. So to kind of preemptively eliminate any confusion, we use explanatory and response. And the explanatory variable may explain or influence changes in the response variable. And the response measures the outcome of the study. And so if you're working for this drug company and this new pill that you've developed might help people lose weight, then the explanatory variable is taking the pill or not taking the pill. The response variable would be the amount of weight that's lost. Now, a scatter plot is a new display. We've already looked at a lot of displays of data so far, but all of those displays have been for a single variable. Okay? We have a set of numbers. Okay? The heights of everybody in the class. That can be represented on stem plot, histogram, whatever method we have, box plot. Those are all single variables. Now with this scatter plot, when we have the coordinate plane, the x value is that explanatory variable, the y value is that response variable. You're comparing two things, and a point on that scatter plot represents an x value and a y value. Okay? So you can read this. We know that the explanatory x is always going to go on the horizontal axis. The response value y is always going to go on the vertical axis. All right? So nothing really new with all of that descriptions there. We talked about this 4-step process that the book likes to embrace. State the plan, okay, the research question of interest, okay, it's the association between the two variables that we're analyzing. The plan would be the solution of your problem by plotting the variables according to the guidelines, and then solving using the scatter plot, taking note of any relationship present. Our conclusions we'll get to a little bit later on. So we have an example here of a scatter plot. It says make a scatter plot of the relationship between body weight and backpack weight for a group of hikers. Okay, so talk about like backpacking where you're carrying all your gear on your back. I was just this past weekend, my wife and my 1.5-year-old daughter and I went to Ohiopyle on Saturday and did a little bit of a hike. I mean, nothing like backpacking through the woods or anything like that, but I have one of these little carriers for my daughter, which she weighs like 27 pounds or something right now, which doesn't seem like much. I mean, you're looking at these values here, but when she's on your shoulders for like an hour and a half, you really start to feel that. So I've never been like the biggest backpacking trip I ever did was like a one-night overnight where you're carrying all your gear and stuff. And I'll tell you what, having the baby on your shoulders is right up there with those long backpacking trips. But we have a relationship here between the hiker's body weight and the weight of the pack in pounds. So you would think that the heavier the hiker, the more weight that hiker could carry. And we see a little bit of a trend here. Okay, we'll talk about those trends momentarily, but every point on this graph represents an explanatory value, the body weight, and the response variable, which is the backpack weight. Okay? 120 pounds for this hiker. The pack weight for that hiker is 26 pounds. Okay? Pretty straightforward stuff. Now, to interpret a scatter plot, you're following the basic strategy of data analysis that we've already talked about in our first couple of sections. You're looking for patterns and important departures from those patterns, possible outliers. Okay? So examining a scatter plot, you're looking for that pattern and striking deviations. You can describe the overall pattern of a scatter plot in the direction, form, and strength of the relationship. And we have a way of measuring those three things into a single number. An important kind of departure is an outlier, an individual value that falls outside the overall pattern of the relationship. And we'll talk about the impact that outliers can have on a scatter plot. Okay, we already talked about that with a single variable in terms of like it can skew the mean, it can pull the mean in that direction. Well, now we have X and Y values, and we'll see what kind of impact an outlier can have in that case. Now, the direction of the association we refer to as either positive or negative. Right? If two things are positively associated, we saw that with the backpacking example. The higher the hiker's body weight, in general, the more weight that hiker could carry. You could also have a negative relationship, right? Where here's your scatter plot. The higher this X value, the lower this Y value. So you could think about something like in terms of the X value is the amount of time you spend studying for a test, and then the Y value is the number of questions you miss on that test, right? You would hope that you would have a negative trend there, and the number of questions that you would miss would be smaller when you're spending a large amount of time studying. Now there's obviously deviations from that, okay? But positively associated, negatively associated values. Or it's possible you could have no relationship whatsoever. Okay? I have these relationships here, and I want us to identify if we think that they're going to be positively associated, negatively associated. They use the word correlation here, which we'll talk about in a second, or no correlation whatsoever. So, what do you think? Calories eaten per day and weight. Positive, negative, or nothing?
Positive.
Yeah, positive relationship. Yeah. In general, the more calories you eat, the higher the weight. Okay? There's deviations from that, but in general, that makes sense that there would be a positive correlation. Calories eaten per day and IQ. What's that?
No correlation.
Yeah, there's no correlation there. Yeah. I mean, there's nothing that really would make sense to us. We don't know what the numbers are in front of us if we actually had data for that, but it seems like there should be no correlation. Amount of alcohol consumed and accuracy on a manual dexterity test. Okay, field sobriety test or something like that. What do you think? Negative correlation. Yeah, the more alcohol consumed, the worse the performance on a test like that. How about this one? Number of ministers, like Christian religious leaders. Number of ministers and number of liquor stores in cities in Pennsylvania. What do you think? No, there actually is a correlation.
Negative correlation?
And it's not negative. There's actually a very strong positive correlation between number of ministers and number of liquor stores in Pennsylvania. Can anybody explain that?
Maybe like population?
Yeah. There's a third variable that sometimes we think about it as a lurking variable, right? We don't want to fall into that habit of causation instead of correlation. There's a correlation here, but it's not that you have a bunch of ministers drinking, meaning that we have a higher number of liquor stores. No, the population is that third variable, that lurking variable, that if you have a large city, you have a number of churches, a number of ministers there facilitating that large population. You also have a lot of liquor stores facilitating that large population. But if it's a more, like Pennsylvania, you got something in like central Pennsylvania, north central Pennsylvania, very rural, then, well, not many churches, not many ministers, not many liquor stores either. Okay, so sometimes it's very enticing to want to blend those two variables together and get that causation implied. Okay, but be careful. Always be on the lookout for these third variables, these lurking variables that might be a better explanation. What about letter E here? Height of the husband and height of the wife. This one's kind of like, you don't really know. Like on one hand, no, tall people marry short people, but you also have two tall people in a relationship, two short people in a relationship. There might be a slight association here. Again, there's no causation or anything like that. If there is a relationship, I'd say it's probably a fairly weak relationship, okay, with a lot of values that don't fit that trend. Now, one of the nice things about scatter plots is that you can introduce additional variables. And we know that we're comparing quantitative data, but you could also introduce categorical variables as well. We have a scatter plot here that's looking at the percent of graduates taking the SAT state by state, and the response variable is the mean SAT math score for those states. So we obviously have the two different colors here, but if this was all just states, we see two distinct clusters in this data set. Okay? These have low percent of graduates taking the SAT, okay, but pretty high math scores, and this would have a higher number of students taking the SAT, but a lower average score. And that would be kind of perplexing to us. And why do we have this great divide? Well, it's actually beneficial in this case that we have the colorization. The red dots represent states in the Northeast. The blue dots represent states in the Midwest. And maybe you know, maybe you don't know, but like the test that's taken for college, SAT or ACT, is very much regionally dictated. In the Northeast, the SAT is more commonly accepted, it's more commonly taken and accepted. So these northeastern states, you have almost all of the graduates taking that test. You've got high-performing students, low-performing students. Their average score tends to be a little bit on the low end. Now, in the Midwest, the ACT is the predominantly taken test. So, in that case, you have very few students taking the SAT. We're looking at numbers in like the single digits or the teens in terms of percentage taking the test. But think about who those students are. They're going to take the test. They're probably like high-achieving students, and their scores are going to be higher. So you don't have those lower performing students going out of their way to take a test that's not common in that region. So these scores on average are much higher. Then you've got Indiana, a Midwestern state that's fitting more with the Northeastern data. Okay? And Ohio over here, which you could argue is, well, they're right next to each other, but Ohio fits better with the Midwestern states. Indiana, I don't know if there's a reason that they don't fit with the rest of their Midwestern states. Okay? So that's an example there. If that was interesting to you, you could explore a little bit further why there's that discrepancy. Scatter plots allow you the freedom to kind of do a whole lot of things. Like, we're going to look at some interesting scatter plots here that, like, the size of the point could mean something in terms of like population. Okay, if you're comparing all the countries, like India, China, they'd have very large dots. Okay, and some of the smaller countries have very small points, and it allows you to introduce multiple variables to analyze and see other trends that might not have been identifiable if everything's just kind of looked at in the same blanketed lens. Okay. Now, to measure a linear association, a scatter plot displays the strength, the direction, and the form of the relationship between two quantitative variables. To measure those three things, we use what's called R, or the correlation coefficient. Okay? I know that you've seen R before. R has a lot of different names. Correlation coefficient, I think it's really called like the Pearson product inertia coefficient or something like that. I can't remember the exact word. I usually just refer to it as R value. Okay? The R value, you know a little bit about R from previous courses. Okay? R is always between -1 and +1. The closer to the extremes, if you had an R value that was exactly 1 or exactly -1, that is a perfect linear correlation. Okay? We call that a deterministic relationship. So if I were talking about like unit conversions, like 12 inches is 1 foot, 24 inches is 2 feet, 36 is 3 feet. Okay? That's a perfect positive relationship. That would have an R value of +1. Okay? Those negative relationships would have a negative correlation. If we have an R value that's close to 0, it's a weak correlation. Now, we're going to let technology calculate an R value for us. Okay? Wednesday, when we meet remotely, we'll be looking at using the calculator, using GeoGebra to help us with these calculations. But, kind of like what we did with standard deviation, I want to show you the equation so you get an idea of what's actually going on with this measure. Okay? It's actually kind of similar to what happened with standard deviation. So every point on this scatter plot has an X value and a Y value. There is also an average of all the X's, a separate average for all the y's. And the x's and y's each have a standard deviation as well. So those averages, those means, it's kind of like what should happen or what you would expect to have happen. So kind of like what we did with standard deviation, you're taking every x value, subtracting away its mean, and dividing by the standard deviation. Do that with the y value as well. y1 minus its mean divided by standard deviation, and you're multiplying those x and y values together. Add on to x2, y2 minus each mean divided by each standard deviation, multiply them together, and then you're on to the next one, and the next one. So you can imagine scatter plot with like hundreds of points, how tedious a calculation like this would be. Okay? We never, ever do this calculation by hand. Okay? Standard deviation, sometimes we'll do it by hand. Okay? You never do that with an R value. Once you get all of those multiplied and added together, you're multiplying by 1 over n minus 1. Okay? Or in sigma notation, you get this value right here. Okay? So, you're getting an idea of what's happening with the trend in that data set. So a positive correlation. Okay? Think of the line of best fit as kind of like what should happen. You get the average x values, the average y values. Some points are above, some points are below. You have an average distance away from what should have happened. That helps dictate the R value. Negative correlations we know are negative. Something with no correlation, again, has an R value that is close to 0. So the data set is completely random, okay, where there's no visible trend. We have no idea where that line of best fit should fall, okay, whether it's going up or down or pretty much horizontal. There is one other thing that you need to look out for, because we know that whether it's positive or negative, that's going along with the slope of the scatter plot, the line of best fit. It is possible that you would have a scatter plot that looks like this, that it's a perfectly horizontal line, but because horizontal lines have a slope of 0, this would have an R value of 0. Okay? You never see that, okay? But kind of like theoretically, that's there as a possibility, which is like the one exclusion for where correlation coefficient could be misleading. Okay? If you have a horizontal line, perfectly horizontal, but there's no slope to it, disguises that as a R value of 0. So here are a couple examples, just kind of get our understanding. We have a graph here that is verbal SAT score as our explanatory variable, GPA as our response variable. And we have an R value 0.485, which indicates, let's say, a moderate positive relationship, right? It's not terribly strong. There's a slight association here. In general, the higher the SAT score, the higher the GPA. But we know that one does not dictate or determine the other. Okay? So, and in fact, this R value is closer to 0 than it is to 1. Okay? So it's a little bit weaker than it is strong. Okay? So it's right there in the middle. A relationship of about 0.5 gives you that moderate relationship. Kind of answering our question we had before. This is two scatter plots here comparing the age of the wife and the age of the husband, and the height of the wife and the height of the husband. Okay, so when we're talking about age, we have age of the wife on the x-axis, age of the husband on the y-axis. We see a pretty good model here, R value of 0.94. That's a pretty strong positive correlation. Obviously, there can be variation there, but all in all, the two do seem to be positively correlated. Talking about the height of the wife, height of the husband, there's a very mild positive association there, 0.36. It's closer to 0 than it is to 1. Okay, so not really a very strong relationship when you're talking about the height as opposed to the age. We have a graph here that is looking at the occupational prestige ranking. So somebody ranks how prestigious your job is on a scale of up to 100, and the suicide rates, which are calculated usually per 100,000 people. So, like if we look at suicide rate of 30, that would mean for every 100,000 people, we have 30 individuals committing suicide in that population. This is from 1970, so things may have changed a little bit, but looking at our data, we have 36 values in our sample. We don't have much of a relationship. In our value of 0.109, you can see that it's pretty spread out. Any line of best fit is almost like horizontal, and we know horizontal lines have a slope that is essentially 0. We do have one value that kind of stands out, which is a fairly prestigious job with a very high suicide rate. Anybody have any guesses as to what this job is? You may have heard this as like a trivia question before. What job, I can't explain it, but what job has the highest suicide rate? Take a guess. It's a dentist. I don't know why, but they say that a dentist is one of the jobs with the highest suicide rates. So if we were to remove that outlier, now you're not always justified in doing that. If you remove that outlier, now that weakens this correlation even further, 0.018. Now it's really pretty much a horizontal line for the line of best fit. Okay, very weak relationship there. We could also have a negative correlation. This is looking at PGA golfers, professional golfers, and the explanatory variable is the length of the putt, and the response variable is the success rate. So this makes sense. If we have a very short putt, we have a very high percentage of success. But as that putt gets longer and longer, that success rate goes down. Okay? So negative relationship here, negative correlation, pretty strong, negative 0.94 for that relationship. Now, some facts about correlation. Correlation makes no distinction between explanatory and response variables. Okay? We have this kind of expectation of, be careful that there's no causation. However, X influences Y. Correlation doesn't see that. It doesn't see any difference. It could very easily just switch them. And in some cases, that explanation might make more sense. Okay? Where you have the Y value actually dictating the X value. Okay? In our next section, we may take a look at an example or two of that. R has no units and does not change when we change the units of measurement of X, Y, or both. Talking about that golfing example and the length of the putt. That putt length was measured in feet. But if we were to measure that in meters or inches or whatever, as long as there's no major rounding discrepancies there, that doesn't change the R value. Okay? R is an artificial measurement. Right? It's a human-made measurement. And we see that a lot with statistics, and sometimes that takes a little bit of thinking about. People aren't used to that. You're used to coming from like physical sciences or physics or chemistry, where every number has a unit that goes with it because it's something that is measured. Well, these are measurements, but they're artificial measurements that we've created to follow these statistical rules. What this value does, we're giving it a scale between -1 and +1, and where it falls on that scale tells us something. Okay? There's no unit that accompanies it. We'll see more measurements like this as we progress through the course. Positive R indicates a positive association. Negative R is a negative association. R is always a number between -1 and +1. We already said that. Some cautions about correlation. Correlation requires that both variables be quantitative. It doesn't make any sense to have categorical data on a scatter plot unless it's that third variable like we saw with the Northeast states and the Midwest states. Okay, but that's not being measured when you're looking at correlation. Correlation does not describe curved relationships between variables, no matter how strong the relationship is. Okay, I know that you probably saw nonlinear models in some of your algebra classes, looking at quadratic models or exponential models. Okay, we could have a scatter plot of data. Looks like this, where I draw my line of best fit. I don't know. Doesn't really make sense there. Doesn't really make sense. Maybe a horizontal line is the best model. This would have an R value of close to 0 because a linear model really doesn't fit this data set very well. But a linear model doesn't really describe what's going on here. Instead, if I were to use a quadratic model, that would be a very nice fit, but that's no longer correlation. Okay? R doesn't work with that. In nonlinear models, we use R squared to talk a little bit about that, but that's not something we're getting into in this section right here. In a statistical sense, most of the relationships that we observe are linear. Okay? There are other cases where we might look at some nonlinear models, but that's for other tests for other days. We are just concerning ourselves right now with linear relationships. R correlation is not resistant. R is strongly affected by a few outlying observations. Okay, we're going to look at outliers in just a second here and what they can do and how they impact the rest of the set and the correlation. Okay, correlation is not a complete summary of the two variable comparison between these in this data. Just like we said with a single variable, you can't just say, here's the mean, and that's the full description. And we needed that full picture about what's going on with the data set. Well, same thing with two variable analysis. Okay? An R value itself, yeah, it tells you something, but there's so much more to be interpreted from that. Okay? Are there outliers? You probably like the scatter plot there to at least visualize what that relationship looks like in addition to an R value. Okay? Now, I have two scatter plots here with different correlations, and each one has an outlier. And I want us to think about how this correlation would be impacted with the presence of that outlier or if that outlier were removed. Okay? So with this data set right here, we have this pretty good linear trend, positive trend, that if we were to ignore that outlier, that's a pretty good fit for that data set. But kind of like the impact that an outlier has on the mean, an outlier with a two-variable analysis, it pulls the line of best fit in that direction. So instead of being right through those points, it's probably going to pull that line of best fit towards the outlier, meaning that now it's not really a good representation of any of those values, right? It had been a pretty good fit before, but now it's pulling that line of best fit towards the outlier, not hitting many of those points at all. This is weakening this correlation. We say that this is inconsistent with the rest of the data. Now, flip that to this case over here. We have most of our data down here, pretty compact, right around there, and then an outlier way up here. Now, if this trend were to continue, we see that that point kind of fits that line of best fit pretty nicely, pretty close. In this case, this outlier is going to strengthen the correlation, which you might not have thought about at first. Right? Typically we think outlier, bad, it's going to make things weak, it's going to make things worse. And that happens from time to time. This is an inconsistent relationship. Okay? We had this trend, low value, low x, low y, high x, higher y. This was inconsistent with that. It was a low x value and a high y value. This trend right here, as x increases, y increases, this has a high x value and a high y value, which doesn't fit the rest of the points, but it does fit that trend if that trend were to continue. I know we haven't talked about it yet in our analysis, but when you're looking at a regression model, you have to be very careful with extrapolating too far beyond what that model was built from. Okay? So if you're doing a line of best fit, you have x values that range from here to here. That line of best fit, or that regression equation, is best used for making predictions between here and here. Sometimes you can justify making a prediction that's a little bit outside that set. But people want to predict the future, right? They want to make predictions about what's going to happen if this trend continues. So what people do is they want to then make a prediction about what's happening way out here, but that model's not built for what happens way out here. All you have information about is from here to here. That's what we see in this case down here. We have a model and an R value that's made for data in this range of x values. But now we have evidence that that trend is going to hold true way out here at this x value. So this is strengthening the correlation because it's actually justifying that this model is going to hold true way out here. So it is strengthening the correlation. Now, you have to be careful in a case like this that it's still an outlier. And you need to go through your analysis of why is that outlier there? And we can't just conveniently dismiss an outlier because it's inconvenient to us when it's a bad outlier. So if it's a good outlier and it's actually helping us and strengthening the correlation, well, you have to be careful about that too. If this were an illegitimate point that just somehow happened to strengthen your correlation, and there's a reason that you should be excluding that, well then that's an ethical violation and you really need to dismiss it. We'll talk about those ethics a little bit later on. An outlier, it requires further inquiry. Okay? Why is that point there? Okay? If it's justified in being removed, then maybe you need to remove that. Sometimes it's consistent with the trend and it inflates the correlation. Sometimes that inflation is artificial. An outlier that is not consistent with the rest of the data can substantially decrease the correlation. We saw that with our previous example there. Someone said that at least 5% of all data points are corrupted when initially recorded or when entered into the computer. We saw that sometimes, like just in class when I'm entering data into the calculator, list 1 on the calculator, like maybe I mean to hit 22 and it actually comes up as 2. Okay? Well, that should stand out. Either I'm looking through the numbers or I see it graphed and I was like, wait, that doesn't fit with the rest of the set. Okay? I go back and I try to explain why it's there. If it's something that I can fix, then I fix it. But if it's a legitimate point, it doesn't matter that it's inconvenient to the rest of my set or it impacts my analysis, it weakens it. If it's a legitimate point, then it needs to remain. But a lot of outliers can just be explained due to data entry. Okay, so clean that up if it's possible. To show you the impact that single values can have, I have a set here that's looking at the nationwide speed limit in miles per hour and the death rate on the highways for every 100 million vehicle miles. So this data was collected in the mid-1980s. And back at that time, there was a gasoline shortage, and the United States implemented a nationwide speed limit of 55 miles an hour to, in theory, help with the fuel efficiency of cars, that you're not eating a lot of gas, exceeding that speed. They said that 55 miles an hour was the most efficient speed. So for a time, we had a nationwide speed limit. That's been rescinded, and now states set their own speed limits, maximum speed limits. But United States had a highway death rate, 3.3 deaths for every 100 million vehicle miles with a 55 mile an hour speed limit. So the speed limit is the explanatory variable, the death rate is the response variable. And you can see we've got a lot of variability in this data set here. We've got Italy stands out as the highest death rate and the highest speed limit, 75 miles an hour. Yeah, when I think of Italy driving, I don't think of having the highest speed limit, right? I either think of like very densely populated Rome, or you think of like very treacherous alpine driving. Neither are really conducive to a really high speed limit, but that's what it is. Maybe it's not a surprise that they have that highest highway death rate. But looking at the rest of this, Britain is the other one that stands out. They have 3.5 deaths, and then 70 miles an hour is their maximum speed. Okay, so let's look at our outliers here. Right now we have a correlation of 0.55, which we said around 5 is or 0.5 is a moderate relationship. Okay, there's a slight positive relationship, a lot of variability, but we see a trend that takes it in this positive direction. What if we had a reason for removing Italy? Okay, if that wasn't typical, let's get rid of it. Now, most of our points are right here, and then Britain's right there. This is a tough one. Okay, maybe you get a slight positive correlation there. If we take Italy out of the picture, that correlation drops to 0.098, just barely above 0. So we have like almost a horizontal line. It has a slight positive slope to it, but that's really not descriptive of any country. Okay? So what really stands out now is Britain. Britain, with its high speed limit, doesn't fit the rest of these countries. Let's take Britain out of it. Now, the correlation jumps back up to 0.7. This is the strongest correlation that we've had yet. Correlation of 0.7 is a pretty good fit. But, again, we're looking at, 8 countries, and we've just removed 2 because they were inconvenient for us. We're not justified in removing outliers because they don't fit with the rest of our set, or we get a better correlation if they're not present. And we have to have a reason for removing them. The purpose of this is really to illustrate how much impact a single value can have. Okay, it can really throw off that correlation, especially across a very small sample size. Revisiting that problem with the age of the husband and the age of the wife. Okay, we have our trend here with a correlation of 0.39. A pretty weak correlation. We have all these values here, the older the wife, the older the husband, but then there was this point right here, where we have a pretty young wife and a pretty old husband, okay, 82 years old. We see that from time to time, right? but it's nothing interesting like that. Instead, this is explained as a data entry error, where the age of that husband was entered as 82, but those numbers got transposed, and it should have been 28. Okay? So here's a case where you look at an outlier, okay, it requires further explanation or exploration, and in this case, you see that no, it was just a data entry error, and you fix that. Okay, now it's 28, brings it back down like right around here, okay, and it fits better with the rest of the data set, and that correlation corrects itself to about 0.964, a very, very strong positive correlation. All right, any questions right now? So, it's not a brand new lesson, as I said. Okay? A lot of this information you've seen before, but especially this stuff talking about outliers and the impact that they can have, interpreting that correlation coefficient, the R value, what that means. Be thinking about that as we move forward. It's more about the analysis than the calculation with some of these things. Okay? Looking at the rest of this week, I will see you on Wednesday remotely, and on Wednesday we're going to be looking at technology, graphic calculator, GeoGebra, for doing this regression analysis and getting this correlation coefficient, the R value. I'll also talk a little bit, if we have people make up the quiz by then, maybe we'll go over the quiz at that point. I know that next time some of you would be here, you guys at home, some of you will be here on Thursday. I will not be here on Thursday. I have an appointment on that day. On Thursday, I have that designated as a work day for us to be working on our assignment that goes with this section. So you don't have to do any homework tonight for this, but that's kind of targeted for Thursday as our time to work on that. Okay? All right. Anybody with any questions right now? All right. Let me